This is chemistry class, Kirtland Central High School. This is reactive lab number 1. This is the first lab where we actually started playing with some chemicals to see what would happen when we had them interact with other elements. Okay, first off though, there was a review of some concepts that we didn't do so well on in the first semester, and we're going to do the whole paper part of the lab. I have part of the chemistry part that we'll do here in just a few minutes. All right. First one, list at least 6 of the 10 laboratory safety rules that we discussed in class. Of course, number 1, most important, is to have some kind of safety glasses or goggles. Now, of course, we also want to have some kind of safety outerwear. That could be a lab coat, it could be an apron when it's appropriate. We want to have closed toe shoes. In my class, depending on the chemicals, I advise my students, as long as it covers the upper part of your foot, if we splash an acid or something on your shoe, we can get your shoe off in time before it burns through to your foot. Because it is a chemistry lab, we also don't want to mix chemicals without supervision. No horseplay. That's kind of a given, but it's sad that we have to put it down. And then, of course, this is number 6, don't smell beakers or test tubes. We want to make sure that any fumes or anything, we're going to waft them to us using that motion with our hands. Some of the other safety rules, of course, don't be in the lab without supervision. Make sure that you clean up after yourself, keep your work area clean, make sure that all glassware is complete and has no cracks or flaws in it. There's several other items that we could add to that list, but this will work just fine. Then we had some safety icons, and we wanted to know their meanings. So the cute little mouse. Oh, and by the way, on this lab, if you've got it, it's down there at the bottom for you to choose from. But we have an animal hazard. That's the cute little mouse there, because when you stick your finger in there, he's going to bite it off. Then this is an apron. Now this, some people said this is a ghost. Woo, it's coming at me. No, it's an apron. So this is, we want to wear some kind of protective outerwear. Could be a lab coat, could be an apron. This one, of course, is the symbol for a rock band or a musical group out there I'm aware of, but no. In chemistry, this is a biohazard, and a biohazard is any organic substance that can be transmitted to a human being. Now, if it's human beings, any bodily fluids, could be mucus out of your nose or mouth, it could be saliva, it could be blood, it could be, well, you get the idea. So, biohazards, anything that can transmit diseases or viruses or germs. The oven mitt here is for extreme hot or cold, because we are going to be working with some things that can get hot or cold. And in this last one, this is a test tube with stuff coming out, so we want to be careful of the fumes. And in the experiment that we did with the sugar and the acid, we had some really vigorous exothermic reactions going on and some really interesting fumes. Next, I asked the students to please walk out into the greenhouse and identify the 5 things that were out there. They included a beaker, a flask, a balance, a set of goggles, and a graduated cylinder. So those are the 5 things that were out there. Excuse me. Next, giving equivalent measurements in each form indicated. We had some issues with equivalent measurements in the fall. And so I wanted to include this to make sure that we all understood what an equivalent measurement was. That's when we're going from one measurement to another, but we're doing the same thing. And then how do we get there? And of course, in science, we want to go to at least 3 places. So at number 1, we want to go from grams to kilograms. Well, here's a couple of rules to keep in mind. When we're going from small to large, we are going to divide. When we're going from large to small units of measure, we're going to multiply. And in this case, you also needed to be aware of your SI measurements. You needed to know what the unit was, meter, gram, liter, because the unit always equals 1. Going up, we have deca, D-E-K-A, that's 10. We had hecto. Hecto is 100. And we had kilo, which is 1,000. This is just the bare minimum. Of course, we looked at the ones that go all the way up to giga, and we looked at all the ones that went down to pico. But coming underneath the unit, then we have deci, D-E-C-I. Now, deci is 1/10, but we don't use fractions in chemistry. We are scientific. We're going to do decimals, so that's 0.1. Centi. Centi is 1/100th, but again, we don't use the fractional. We're going to use the decimal, 0.01. And then, of course, there's milli. Yeah, everybody knows milli. 1/1000th, and on that one, 0.001. Always, 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 we're going to use the decimals in chemistry. So let's go back to our questions now. 2,000 grams to kilograms. Very simply, to set this up, 2,000 divided by 1,000. 2,000 divided by 1,000 is 2 kgs. All these zeros go away. 2 over 1, the fraction of 2 over 1 becomes 2. 100 kilometers to meters. Well, there's 1,000 meters in a kilometer. And so we're going to multiply 100 times 1,000. And again, the metric system being what it is, it's all 10 based. And if you know how to manipulate the zeros, you can do this very easily. 1, 2, 3, 4, 5 zeros in the answer. 1, 2, 3, 4, 5 zeros in the answer. 1 times 1 is 1. 100,000 meters. Now, I already know. I can hear you. There's somebody out there. What did he do? It's magic. It's voodoo. What did he do? Well, here we go. I'll do this for you right now. 100 kilometers times 1,000 meters per kilometer is 100,000. 1, 2, 3, 4, 5 zeros and a 1. It's the same answer. So we got there. We just did it a different way. Let that one sink in for a second. All right, 1,234 meters in a kilometer. Again, we're going to go from small units to large units, so we're going to divide. We can divide that one by 1,000. Now again, these cancel out, so it's going to be 1 over 1, so that's 1.234 kilometers. I know, again, here we go. I got you covered here, no problem, because you guys have to see it on a calculator. Sometimes, not a big deal. 1,234 divided by 1,000 is 1.234. 1.234. We gotcha. 1,326,418 grams in a kilogram. Well, again, we're going to divide that by 1,000. So this one becomes 1,326.418 kilograms. These 3 zeros, those 3 go away. Here's where our decimal point is going to go. I know. I hear you. Please, I got you. 1,000 or 1,326,418 divided by 1,000 is 1,326.418. 1,326.418. We got the correct answer. All right, going to go backwards on this one. we have 1.4625 kilometers into meters. We're going to multiply this times 1,000. Okay. Now again, if we know what to do with the zeros here, we're going to start right here. 1, 2, 3. This becomes 1462.5 meters. Well, let's just check that out and make sure. 1.4625 times 1,000 equals 1,462.5, and there we have it. So that was the math and the equivalent measurement. We go over here now. This is the National Weather Service wind chill chart. As you can see, it's color-coded. Now this one is unique because down the y-axis, this is the wind speed, and across the x-axis on the top is the temperature, and then across the bottom it tells us about frostbite. Frostbite, in case you're not aware, is when you're out in the cold and it is so cold that the cells of your body actually begin to freeze. Your body begins to freeze. And elementary science, we know that water, when water, the H2O molecule, and that H2O is the two H's and an O in kind of that configuration. We know when these freeze, these expand out. And so this is why ice floats, is because these H's, these bonds, become longer. If ice did not float, it would all sink to the bottom of the ocean, and eventually we'd be nothing but an ice-covered ball floating in space. Well, what happens in your body is when these atoms expand, this molecule expands, it will actually burst the cells of your body, destroying the tissue. So that's why this wind chill chart is very important. The only thing that's not on here is this white area, frostbite times. This area here is 30 minutes. This area here is 10 minutes till frostbite, and this area here is 5 minutes to frostbite. This white area, they didn't tell us what it was, so we're going to do white, and white is going to be greater than 30 minutes. We're going to use the greater than. Remember, alligator eats the big one, so this must be greater than 30 minutes because it's bigger. Alligator's eating it. Okay. When the air temperature is 40 degrees and the wind is blowing 5 miles per hour, air temperature is 40, wind is 5, that must mean it is 36 outside, 36 degrees Fahrenheit. That's the answer to that one. And the wind is blowing 30 miles an hour and the air temperature is 0. What does that feel like? Well, 30 miles an hour, 0. Did I say 0? And the temperature is 0. What does that feel like? That's going to feel like 26 degrees below 0. Now here in New Mexico, for those of you watching from outside the state, the lowest temperature ever recorded in New Mexico is in the 1950s in a little community called Lindrith. Lindrith is kind of in northwestern New Mexico, and it was over 50 degrees below 0. Me personally here in New Mexico, the coldest I've ever been involved with is about 40 below 0, and that was at Dulce, New Mexico in 2011. I've also been to 34 below at Navajo, New Mexico, and that was in 1989. And we had about 20 below 0 at Bernalillo, New Mexico when I was in high school, and I won't tell you that was in about the 1970s. So it can get cold here in New Mexico. Next one, air temperature is 15, wind is 45. 15 temperature outside, wind is 45, it's -9. But it wants to know what's the apparent temperature, it's -9. Then it wants us to infer or interpret. The colder the air temperature, the stronger the wind is blowing, the colder, the more intense, whoops, misspelled intense, the worse the wind chill. You get the idea. Anything's acceptable if it gets that message across that when you're going this way, this gets really bad over here. If the air temperature is 20 and the wind speed is 30, 20 and 30, it says, how long until my exposed skin suffers? Well, the wind is blowing 30 and it's 20 outside. That means it's 1 degree. It's in this white area, so this should be greater than 30 minutes. Then it says if the wind is blowing 40 and the air is minus 20, how long can I be out and exposed before frostbite sets in? And by exposed, we mean no shoes, no gloves, no hat, probably not even a heavy coat, but lightly dressed. So if it is, let's run that again, 40 miles an hour and the temperature is 20 below. 20 below is this line here. 40 miles an hour is this line here. They intersect at 57 degrees below zero. I can be outside approximately 5 minutes before I start freezing to death. And in most cases, when it's that cold, I'll probably be unconscious in less than 15 minutes, and I'll probably be dead in about 30. Okay, next, this one has to do with percentage of error. And many students did not do this final part because I guess there wasn't a line there and they didn't realize you're supposed to do it anyway. But the mass of a brass cylinder is 100 grams. When you put the cylinder on a balance and measure it, the mass is indicated at 102.3 grams. What's the difference between the given or accepted mass and the actual or experimental mass? Well, really simple. 102.3 minus 100 equals 2.3 grams. What's the percentage of error between the actual measured mass and the given mass? Well, I have the instructions right here for doing it. Subtract the actual from the given. We did that. That's this answer here. Divide that answer by the accepted value. So we're going to do 2.3 divided by the accepted value is supposed to be 100. That gives us 0.023. Excuse me, I got something in my throat this afternoon. Then we multiply that answer times 100, and we get an answer, and we put a percent sign behind it. Well, if you already saw what we did, we're just doing this backwards. We're going to end up at 2.3% is the error. That's the difference between the actual mass and what we're supposed to have. And so now we're going to predict reactions. This is where we get into the chemistry part. We're working in our chemistry book, and we've just started learning basic reactions and basic compounds. And so when I put this question in front of them, we haven't really covered this yet, but I wanted to know, could you kind of predict what we're going to get on the back side of this experiment? And so, here we go. First off, we're going to be combining H2SO4. H2SO4 is sulfuric acid, byproduct of a lot of processes, especially from the oil and energy industry. I don't even know if I'm going to be able to finish this. I'm coughing so bad. There we go. A little more water. I'm going to tough this out. I'm almost there, everybody. We're going to make it one way or the other. Let me reach across here for a second. All right, just a second. I got to turn around and cough really bad. I don't want to pause the video. My apologies. I'm very sorry for doing this. All right, we're going to mix sulfuric acid and iron, in this case iron 1. Remember, the Roman numeral indicates if it's a variable ion atom, in this case 1 extra electron. Well, if we combine hydrogen and sulfur, at some point we can probably get a water off. We might get some H2SO, hydrogen sulfate.